120 light-years from Earth, in the constellation Leo, a telescope caught something that shouldn't exist. The James Webb Space Telescope detected a world where the temperature stays locked at 49 degrees Celsius, warm enough for liquid water, stable enough for chemistry to thrive, and wrapped in an atmosphere that carries a molecule we've only ever seen produced by one thing: life. Dimethyl sulfide. On Earth, plankton make it, bacteria make it. It doesn't come from volcanoes or lightning strikes or random chemical reactions. Only living organisms produce it. The signal wasn't weak. The probability of error was calculated at less than 0.3%. Scientists don't use language like certain very often, but this time they did. 99.7% confidence. In most fields, that's as close to proof as you can get. If you're interested in where this discovery leads, subscribe. It helps the channel grow, and there's a lot more to uncover here. This isn't just another exoplanet. This is the first time we've measured life beyond Earth with near certainty. The numbers are real, the chemistry checks out, and the implications go further than most people realize. So let's start with how it happened. Part 1. The moment of discovery. The data arrived on a Tuesday morning in December. At Cambridge University, astrophysicist Niku Madhusudhan was reviewing light curves from the James Webb Telescope. He had been studying this planet for months, watching the faint dips in starlight as it passed in front of its star. Each transit revealed a little more about the atmosphere. Water vapor showed up first, then methane, then carbon dioxide. Standard stuff for a planet this size. But then the spectrograph flagged something unusual, a specific absorption line that didn't match any of the expected molecules. Madhusudhan ran it through the database again, then a third time. Dimethyl sulfide. He stared at the screen for a long moment. There's no known geological process that creates it, no volcanic outgassing, no atmospheric chemistry that can explain it without invoking life. The detection was strong, 3 sigma confidence, which in statistical terms means 99.7% certainty, the same threshold physicists use when they discover new particles, the kind of number that doesn't leave much room for doubt. Madhusudhan's team spent the next few weeks trying to break their own findings. They checked for contamination from Earth's atmosphere. They ran simulations of every non-biological process that might produce a false positive. They consulted chemists, planetary scientists, astrobiologists. Every alternative explanation fell apart. The planet is called K218b. It orbits a red dwarf star in Leo, roughly 8 times the mass of Earth, which puts it in a category astronomers call a sub-Neptune. For years, planets like this were assumed to be hostile to life. Too much hydrogen in the atmosphere, too much gravity, not rocky enough to support complex chemistry. Webb's data suggested otherwise. The thick hydrogen atmosphere acts like a thermal blanket, trapping heat and distributing it evenly across the surface. No extreme seasons, no ice ages, just steady, predictable warmth at around 120 Fahrenheit. And somewhere in that stable environment, something is producing dimethyl sulfide. The announcement went out quietly at first, a preprint paper, a few cautious interviews, but within days, the scientific community understood what they were looking at. This wasn't speculation anymore, it was measurement. For the first time in history, we had hard evidence of life beyond Earth. Part 2. Portrait of the planet K218b. K218b is not like Earth. It's 8 times more massive, which means the gravity at the surface is roughly twice what we experience here. If you could stand on it, you'd weigh twice as much. The atmosphere is thick, dominated by hydrogen and helium, nothing like the nitrogen-oxygen mix we breathe. The pressure near the surface is intense, possibly hundreds of times greater than at sea level on Earth. But despite all that, it might be more habitable than our own planet. The star it orbits is a red dwarf, much smaller and cooler than the Sun. Red dwarfs are the most common type of star in the galaxy, and they burn slowly. Our sun will last about 10 billion years. A red dwarf can burn for trillions. That gives any life that starts there an almost unimaginable amount of time to evolve. K218b sits in the habitable zone of its star, the region where temperatures allow liquid water to exist. But the stability goes deeper. The hydrogen-rich atmosphere doesn't just hold heat, it redistributes it. There are no violent temperature swings between day and night, no runaway greenhouse effect. The whole system seems balanced in a way that Earth, with its ice ages and mass extinctions, never quite achieved. Water is almost certainly present. Webb detected water vapor in the atmosphere, and the planet's density suggests there could be oceans beneath the hydrogen layer. Not shallow seas, but deep water, possibly hundreds of kilometers down. In those depths, shielded from radiation and kept warm by atmospheric pressure, chemistry could unfold without interruption. The missing gases tell their own story. If K218b were lifeless, its atmosphere should be full of ammonia. Ammonia forms naturally in hydrogen-rich environments, but Webb found almost none of it. Something is removing it from the air, converting it into other compounds. On Earth, microbes do exactly that. They pull nitrogen from ammonia and use it to build proteins. The methane levels are also off. Methane usually breaks down quickly under ultraviolet light, but K218b has steady amounts of it in the atmosphere. That suggests a constant source, something replenishing it faster than it can decay. Biological processes are one of the few things that can maintain that kind of imbalance. Then there's the carbon dioxide and water vapor, both present in ratios that don't quite match what you'd expect from a dead world. Together, these gases create what scientists call a chemical disequilibrium. The atmosphere is out of balance, and the only known explanation for that is life constantly reshaping its environment. This isn't a frozen ice ball or a scorched desert. It's a world where conditions have been stable for potentially billions of years. If life started there, it didn't have to fight for survival against constant catastrophe. It just had to exist. And the evidence suggests it does. Part 3. How Webb Saw It. Detecting life from 120 light-years away requires technology that borders on the impossible. The James Webb Space Telescope orbits at a point called Lagrange 2, about 1 million miles from Earth. It's a gravitational balance point where the pull of the Earth and Sun cancel out, letting the telescope stay in one place with minimal fuel. Out there, it lives in permanent shadow, shielded from the sun by a 5-layer sun shield the size of a tennis court. The telescope has to stay cold, colder than the surface of Pluto. If it warmed up even slightly, its own heat would drown out the faint infrared light it's trying to detect. The heart of Webb is its mirror, 18 hexagonal segments coated in gold. Together, they form a surface so precise that if you scaled it up to the size of the United States, the biggest imperfection would be less than an inch tall. That precision matters because Webb is looking for signals that are almost impossible to see. When K218b passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere. Molecules in that air absorb specific wavelengths, leaving gaps in the spectrum. By measuring those gaps, Webb can identify what's in the atmosphere. It's like reading a chemical fingerprint written in light. The problem is that the star is billions of times brighter than the planet. To isolate the planet's signal, Webb uses a coronagraph, a mask that blocks the star's glare. What's left is analyzed by instruments so sensitive they can pick out a handful of meaningful photons from millions of random ones. The light Webb captured from K218b left that planet 120 years ago, around the time humans were just starting to experiment with radio. It traveled across interstellar space while we went from the Wright brothers to the moon landing to building telescopes that could see it arrive. Each photon carries information. The wavelength tells you which molecule absorbed it. The strength of the absorption tells you how much of that molecule is present. By comparing thousands of these measurements, scientists built a map of the planet's chemistry. Dimethyl sulfide showed up as a clear absorption line, not faint, not ambiguous, strong enough that the statistical analysis returned 99.7% confidence. That's not a guess. It's not a hopeful interpretation. It's what the data says. Webb also detected methane, carbon dioxide, and water vapor, all in concentrations that don't make sense without biological activity. The ratios are wrong for a lifeless planet. They're constantly shifting, which means something is actively producing and consuming these gases. The entire detection process took months. Each transit of the planet was measured, cross-checked, and compared with atmospheric models. The team ran simulations to see if any non-biological process could explain the signals. None could. What Webb found wasn't just chemistry, it was behavior, an atmosphere that acts like it's alive. Part 4. The chemistry of life. A dead planet's atmosphere settles into equilibrium. Gases react with each other until they reach a stable state, and then nothing changes. You get predictable ratios of methane, carbon dioxide, nitrogen compounds. Everything balances out according to temperature, pressure, and basic chemistry. K2-18b's atmosphere doesn't do that. The methane levels are too high. Ultraviolet radiation from the star should be breaking it down constantly, but the concentration stays steady. That means something is replacing it as fast as it disappears. On Earth, microbes in swamps and oceans produce methane as a byproduct of metabolism. It's one of the oldest biological processes we know. The carbon dioxide levels fluctuate in ways that suggest active consumption. If the planet were geologically active, volcanic outgassing might explain some of it. But K2-18b doesn't show signs of the kind of tectonic activity that would sustain that. The most likely explanation is that organisms are pulling carbon dioxide out of the air and converting it into organic compounds, the same way plants do here. Water vapor is present, but not in the amounts you'd expect if the oceans were just evaporating passively. The distribution across different altitudes suggests something more complex is happening, possibly a cycle driven by biological processes in the water below. And then there's the ammonia problem. Ammonia should be everywhere in a hydrogen-rich atmosphere like this. It forms naturally from nitrogen and hydrogen, and once it's there, it's hard to get rid of. But Webb found almost none. On Earth, bacteria consume ammonia and use the nitrogen to build proteins and DNA. If the same thing is happening on K2-18b, it would explain why the ammonia is missing. Dimethyl sulfide is the strongest piece of evidence. There's no known way to produce it without biology. Volcanic gases don't contain it, lightning doesn't create it, you can't make it through photochemistry or mineral reactions. Every sample of dimethyl sulfide we've ever analyzed on Earth came from living organisms. The presence of all these gases together creates what's called a chemical disequilibrium. The atmosphere is constantly being pushed away from balance by processes that consume and produce specific molecules. That's the signature of life. It doesn't allow the environment to settle, it reshapes it continuously. Scientists ran dozens of models to see if any combination of geology, atmospheric chemistry, or stellar radiation could mimic this pattern. None of them worked. The simplest explanation, the one that fits all the data, is biology. That doesn't mean we know what kind of life it is. It could be single-celled organisms floating in the upper atmosphere. It could be microbial mats covering vast underwater surfaces. It could be chemistry we don't even have a name for yet. But it's doing something, and that something is leaving traces we can measure from across interstellar space. Part 5. What might live there? If there's life on K2-18b, it's probably not walking around. The gravity alone makes complex multicellular organisms unlikely. Twice Earth's gravity means everything weighs twice as much. Bones would need to be thicker, Muscles would have to work harder just to move. Evolution tends to favor efficiency, and under those conditions, staying small makes more sense. The most likely candidates are microbes, single-celled organisms that float in the atmosphere or cluster in the deep oceans beneath the hydrogen layer. On Earth, extremophiles thrive in conditions we once thought were impossible. Bacteria live in boiling hot springs, in Antarctic ice, in the crushing pressure of ocean trenches. Life finds a way to adapt to almost anything. On K2-18b, the chemistry would be different. The atmosphere is full of hydrogen, which means organisms there might use hydrogen as an energy source instead of oxygen. Some bacteria on Earth already do this. They're called hydrogenotrophs, and they pull energy from hydrogen gas the same way we pull energy from oxygen. The oceans, if they exist, would be strange. Water mixed with hydrogen under extreme pressure creates conditions we can't easily replicate in a lab. The chemistry down there could support metabolic processes we've never seen. Organisms might harvest energy from chemical gradients, from the slow mixing of different layers, from minerals dissolved in the water. There's also the question of how life started in the first place. On Earth, the leading theory is that it began in hydrothermal vents on the ocean floor, where hot mineral-rich water met cold seawater and created the right conditions for complex molecules to form. K2-18b could have something similar. Deep beneath the hydrogen atmosphere, where pressure and temperature create a kind of chemical laboratory, the first self-replicating molecules might have assembled themselves billions of years ago. Once life started, it would have had time to spread. Red dwarfs live for trillions of years, and K2-18b has likely been in the habitable zone for most of its existence. That's far longer than Earth has had life. If microbial ecosystems developed there, they've had geological ages to diversify, to fill every available niche, to reshape the planet's chemistry on a massive scale. The dimethyl sulfide suggests that whatever is living there has already developed fairly complex metabolic pathways. Producing that molecule requires specific enzymes, specific biochemical processes. It's not the kind of thing that happens by accident. Could there be anything more advanced? Maybe, but the conditions don't favor it. High gravity, thick atmosphere, intense pressure near the surface, all of these make it harder for large organisms to evolve. Intelligence requires energy, and energy is expensive when you're fighting against gravity just to exist. What's more likely is a planet-wide microbial ecosystem. Trillions of organisms cycling gases, consuming nutrients, reproducing, dying, feeding each other. A living planet in the most fundamental sense. We won't know for sure until we can study it more closely, but the chemistry is already telling us that something is there, altering the atmosphere in ways that only life can explain. Part 6. Next steps. One detection isn't enough to close the case. Webb's data is strong, but science requires confirmation. Other telescopes need to see the same signals. Different instruments, different methods, different teams analyzing the same planet independently. That's how you rule out systematic errors or equipment malfunctions. The next step is already underway. NASA's upcoming Habitable Worlds Observatory is being designed specifically to study planets like K2-18b in more detail. It will have better resolution, more sensitive spectrographs, and the ability to observe multiple transits over longer periods. If the dimethyl sulfide is real, HWO will confirm it. The Nancy Grace Roman Space Telescope, set to launch in the next few years, will also contribute. It's designed for wide-field surveys, which means it can scan large portions of the sky looking for other planets with similar atmospheric signatures. If K2-18b isn't unique, Roman will find the others. Ground-based observatories are joining the effort too. The extremely large telescope in Chile, once it's operational, will have a mirror 39 meters across. That's enough collecting area to study exoplanet atmospheres in far greater detail than Webb can manage. It won't replace space telescopes, but it will add another layer of data. What scientists are looking for now is oxygen. Oxygen is harder to fake than dimethyl sulfide. It reacts with almost everything, so if you find it in large quantities in an atmosphere, something has to be constantly producing it. On Earth, that something is photosynthesis. Plants, algae, cyanobacteria, they all split water molecules and release oxygen as waste. If K218b has oxygen in its atmosphere, that would be nearly impossible to explain without invoking photosynthetic life. Combined with the dimethyl sulfide, it would push the probability of life even closer to 100%. There's also the question of variability. Does the dimethyl sulfide concentration change over time? Seasonal variations could indicate biological cycles, organisms responding to changes in temperature or light. Long-term trends might show evolutionary shifts, ecosystems adapting to slow changes in the planet's climate. All of this takes time. Each observation requires careful planning. The telescope schedules are booked years in advance, and every hour of observation time is competed for by dozens of research teams. Getting enough data to confirm or refute the findings could take a decade. But there's also the possibility that the hypothesis is wrong. Maybe there's a geological process no one has thought of yet. Maybe the spectral lines are being misinterpreted. Maybe contamination from an unexpected source is mimicking the signal. Science has to leave room for those possibilities, even when the evidence looks solid. The team that discovered the dimethyl sulfide has been transparent about this. They published their methods, shared their data, and invited scrutiny. That's how the process works. If someone finds a flaw, the hypothesis gets revised or discarded. For now, though, the evidence holds, and every follow-up observation will either strengthen it or reveal where it breaks down. Either way, we'll know more soon. Part 7. The Future, What It Changes. If the discovery holds up, it changes how we search for life. For decades, astronomers focused on Earth-like planets orbiting Sun-like stars, rocky worlds with thin atmospheres, moderate temperatures, oceans on the surface. The assumption was that life required conditions similar to ours. K218b breaks that model. It's a sub-Neptune with a hydrogen atmosphere orbiting a red dwarf. Nothing about it resembles Earth, and yet it might be teeming with life. That opens up an entirely new category of habitable worlds. Planets we used to dismiss as too hostile could now be priority targets. Red dwarfs make up about 75% of all stars in the galaxy. If their planets can support life, the number of potentially habitable worlds just increased by orders of magnitude. We're not looking at a few dozen candidates anymore. We're looking at billions. The implications go beyond astronomy. If we confirm that life exists on K218b, it will be the first time in human history that we've proven we're not alone. That shifts the conversation in fields ranging from philosophy to law. The Outer Space Treaty, written in 1967, was designed to govern territorial claims and prevent weaponization of space. It says nothing about how to handle the discovery of living ecosystems. New policies will need to address contamination. If we ever send probes to K218b, we'll have to ensure they don't carry Earth microbes that could disrupt an alien biosphere. The same planetary protection protocols we use for Mars will need to be extended to interstellar missions. There's also the question of rights. Does a microbial ecosystem have intrinsic value? Should it be protected from exploitation? These aren't just ethical questions. They'll have legal and political consequences as space exploration becomes more accessible. For the general public, the impact might be subtler but just as profound. Children growing up in the next few decades will learn about K218b in school. They'll see images of its parent star, read about the chemistry in its atmosphere, and understand that life exists beyond Earth. That knowledge becomes part of the baseline, not a shocking revelation. The night sky stops being empty. Every red dwarf becomes a potential home for biology. The question shifts from, are we alone, to how common is life and what forms does it take? Astronomers are already planning missions that would have seemed absurd a generation ago. Concepts like breakthrough starshot propose sending tiny laser-driven probes to nearby star systems at a fraction of the speed of light. The technology isn't there yet, but the discovery of life elsewhere makes the investment easier to justify. Closer to home, new propulsion systems are being tested. Fusion drives, advanced ion engines, solar sails. Each one brings interstellar travel a little closer to feasibility. If we know there's life out there, the motivation to reach it becomes stronger. But the real shift is conceptual. For most of history, humanity saw itself as the center of the story. The universe was backdrop, something to explore or conquer. Discovering life elsewhere changes that. The cosmos becomes a community, a network of living systems, each shaped by the same physical laws, each experimenting with different solutions to the problem of survival. We're not the main character anymore. We're one participant among many. The light that reached Webb's mirrors began its journey 120 years ago. It left K2-18b while humanity was still learning to leave the ground, carrying within it the faint trace of an atmosphere that breathes. By the time it arrived, we had built machines capable of reading its message. We didn't find life at the moment it began. We found an echo, a signal from a world that's been alive for who knows how long. The dimethyl sulfide detected in that light might have been produced by organisms that lived and died generations before the photons even reached us. That's the strange thing about astronomy. You're always looking at the past, but in this case, the past is telling us something about the present. If life was there a century ago, it's almost certainly still there now. The discovery won't be fully confirmed for years. More observations, more data, more scrutiny. But the evidence is already stronger than most scientists expected to see in their lifetimes. We used to think the universe was silent, that Earth was an exception, a rare accident in an otherwise sterile cosmos. Webb showed us we were wrong. The universe isn't mute. It's been speaking in chemistry, in the shifting balance of gases, in patterns that whisper of something more than rock and radiation. K2-18b is probably the first of many. Each new detection will make the picture clearer, until the question isn't whether life exists elsewhere, but how common it really is. If you enjoyed this, leave a like and subscribe to keep exploring the cosmos with us. There's a lot more out there, and we're just starting to learn how to listen. See you in the next one.